Good evening, everyone. I am Karan Ahuja, a fourth-year PhD student at the Human-Computer Interaction Institute of Carnegie Mellon University. Today, I'm going to talk to you about my work on directional voice estimation for intuitive speech interaction with smart device ecosystems. This work was done with my collaborators Andy Kong, Mayank Goel, and Chris Harrison at CMU. Where a person is looking is an important social cue in human-human interaction, allowing someone to address a particular person in a conversation or specify a focus of interest. Prior computing systems that have used gaze location have either used sensors worn on the head, unlikely for consumer adoption such as the DoV eye tracker, or cameras which have significant privacy implications in settings such as homes. In this research, we explored whether speech could be used as a directional communication channel, much like visual gaze. This can be seen in the demonstration of our system here.
How's the weather? How's the weather?
Today, voice user interfaces have entered the mainstream via smart assistants such as Google Home or Apple Siri, and products such as smart speakers, smartphones, and smartwatches. They have proliferated to almost all devices around us. However, these devices simply receive and process spoken content, irrespective of if they were the intended target. In these cases, the directional voice will provide a natural mechanism for disambiguation. Note, this is different from existing direction of arrival algorithms, which calculate from where a voice originated. In this example, the direction of arrival between the speaker and the smartphone would be the same, irrespective of the user's orientation to the device. In contrast, our approach calculates the direction along which a voice was projected. This innately enables voice commands with addressability in much the same way as gaze, but without the need for cameras. This not only allows users to dispense with wake words, but also more readily and naturally interact with increasingly dense ecosystems of smart devices. What this inherently boils down to is predicting where the user is facing or the head orientation of the speaker based on the audio data. That way, we can tell whether the user is facing the device or not for the intents of interaction or other applications. We are not the first ones to think along these lines. Let's first take a look at the prior work in this area. Prior systems have looked at placing multiple microphones around the room. Nakajima et al. Makes use of 96 microphones embedded in the walls of a room. Works by Seguro et al. Further reduces the number of mics needed using 6 T-shaped microphones clusters in a room of known geometry. Recently, in parallel to our approach, Yang et al. Made great strides in this area and presented SoundR at CHI 2020. They make use of raw audio from a single microphone array and employ a CNN plus LSTM-based deep learning architecture to estimate the speaker's position and head orientation. We provide a complementary approach using a single microphone array wherein we pursue a featurization approach that is informed by the physics of sound propagation and the human vocal tract. Our setup consists of a 4-channel mic array, with each channel sampling audio at 48 kHz. Our approach relies on 2 fundamental properties. Let's go back to the room that we took as an example to see what they are. The first is that built environments introduce characteristic multipath effects. When a user speaks towards a device, the first, loudest, and least distorted signal to arrive is the original sound, which took a direct path. All other sounds, which have echoed and scattered off of various surfaces in the environment, are delayed, quieter, and more distorted. We measured this multipath effect by the crispness of the first wavefront and narrowed down on 3 key types of features which capture this. First, and most straightforward, is to run autocorrelation on the sound. If we receive a facing sound that came first and directly to the microphone, there should be no echoes on which to correlate against in the first few milliseconds of audio. As a measure of reverb, we calculate the speech to reverberation modulation energy ratio. Finally, we also compute the cross-correlation using the generalized cross-correlation with phase transform algorithm between all the 6 pairings offered by our 4-channel mic array. You can see the difference in correlation between facing and not facing on the image on the slide. The second property on which our approach is built is that the distribution of human speech frequencies varies by spoken angle. The figure here shows the frequency-dependent polar plots from 160 Hz to 8 kHz. In particular, higher frequencies are more directional and also tend to be absorbed by the environment, leaving the more omnidirectional lower frequencies to reach the microphone. This creates a characteristic imbalance between higher and lower speech frequencies that you can see on this FFT. We encode this data by capturing the sum power of low and high frequencies, the ratios between them, and also by fitting a polynomial to the FFT to capture its shape and taking its coefficients as its features. An end-to-end demonstration of our system can be seen here, where the user faces the microarray placed on the countertop and speaks to it from different body orientations. The predictions are displayed on the laptop where the processing is happening.
When does my bus come? When does my bus come? How is it outside?
In the future, the processing could be entirely done on a smart speaker as our system is lightweight and computationally tractable. Now, I've used the word facing the microphone a lot till now. What does it actually mean? There is no universally accepted definition of what constitutes as facing a direction. Therefore, we ran a pilot human benchmark study to understand what directions constitute as facing and also provide a preliminary insights into how well humans can estimate direction of voice. For this, we recruited multiple pairs of participants. For each pair, one listening participant sat blindfolded, mimicking a microphone, and the other participant spoke towards them from different angles. For each of these angles, the listener predicts whether the speaker is facing them or not. Here, you can see the accuracy for each of these angles, for which the listener thinks the speaker is facing them. It is interesting to note that even when the speaker is unambiguously facing the listener, 6% of the participants think that the speaker is not facing them. This helps us to establish a human baseline and also shows the complexity of directional voice estimation. Based on our findings, we modeled 3 definitions of facing. Directly facing, where 0 degrees is facing and everything else is not facing. Forward facing, where this notion of facing is between plus minus 45 degrees. And mouth line of sight, where the notion of facing expands to plus minus 90 degrees. In order to analyze the efficacy of our system across different factors, we collected data from 10 participants in 2 back-to-back sessions, wherein the user spoke 2 utterances, namely "Hey assistant" and "The quick brown fox jumped over the lazy sheep," across 2 rooms, a classroom and an office, and 2 device placements, one against the wall and one away from it. We collected this data across 3 user distances, as can be seen on the image on the right, 1 meter, 3 meter, and 5 meters. At each distance, there were 3 polar positions, and each position had 8 orientations, starting from 0 to 360 degrees at 45-degree increments. The directional voice arrow is highlighted in black at each of these positions. Such a setup allowed us to bin outputs based on the different definitions of facing that we discussed. This resulted in a total of 11,520 recordings being collected with over 350 minutes of data. For our machine learning algorithm, we used an extra trees classifier. We trained our classifier across all 8 angles of direction of voice to mitigate class imbalance and binned the output predictions based on the facing definition we were testing on. We designed a study procedure in order to systematically isolate and analyze different factors. These graphs showcase the accuracy of our system across different factors. As this is a lot to process, for both brevity and clarity in all subsequent slides, we are only going to talk about forward-facing criterion. For full results, please refer to the paper. There are 2 key takeaways from this plot. The first is that our accuracies are in line with human benchmarks, showcased here in purple stripes. The second is that we do not see a huge accuracy shift across different placements, people, or utterances, which is great for the generalizability of our model. We started off by purposefully engineering our machine learning features to be speech invariant. To explore how successful we were, we reduced the dimensionality of our feature set to 2 components using a linear discriminant analysis. You can see on these plots there is little difference in the distribution of different spoken angles, a positive result suggesting generalizability. This means that you can train our model on a few utterances, like we do for Siri or Google, and then it can make a voice profile for you that generalizes to different utterances. Another perk of our approach is that apart from utterances, it can work across different languages as well. Here, we make use of our model trained on data we collected in English and test it on utterances in Chinese.
今天怎么样？今天怎么样？
And Spanish.
¿Qué tiempo hace? ¿Qué tiempo hace?
We found that distance has a profound effect on the accuracy of our system, as can be seen in these LDA plots. Results show accuracy at 1 meter away is 97%, dropping to 93% at 3 meters, and finally 88% at 5 meters. Looking at information loss, we find that features derived from voice frequency distribution drop the most in value at longer distances. It is important to note, while our system has promising results, there are several key limitations before it can be ready for consumer adoption. First is the accuracy of the system itself. Our model can distinguish between speakers facing and not facing a device at about 90% accuracy. However, it does fall short of the 99% plus accuracy consumers have come to expect, though they are perhaps more forgiving with voice interfaces. We also acknowledge our current implementation does not attempt multiple speaker directional voice estimation, which would preclude its use in highly social settings. Currently, voice interfaces that rely on wake words are susceptible to false triggers. This can be due to external media sources such as your TV saying the wake word such as "Hey Alexa" or incorrect wake word prediction. For example, when someone says "Hey Sarah" and your Siri gets activated. These cases can be as high as 10%. In such cases, directional voice estimation can be combined with wake word confidence to increase robustness to false triggers. Thank you for listening. This concludes my presentation. For any questions, please feel free to mail me at the email ID shown on the slide.